My name is Mike Cosh, and I am a research hydrologist at the Hydrology and Remote Sensing Laboratory in Beltsville, Maryland, and I'll be discussing Component 4, Watershed Management to Improve Ecosystem Services in Agricultural Landscapes. Integrated watershed management is a complex task that supports not only regulatory goals, such as the Clean Water and Endangered Species Acts, but also addresses the concerns of farm communities, water districts, watershed coalitions, policymakers, and the public in general. There is an obvious need to establish long-term experimental sites. In 2011, ARS established the Long-Term Agro-Ecosystem Research Network, or LTAR, which is composed of 18 sites around the U.S. This network includes most of the ARS experimental watersheds, some dating back to the 1950s. This national network enables the development of integrated watershed management strategies for agriculture across broad regions of the continental U.S. Component 4A is titled Improving Watershed Management and Ecosystem Services through Large Area Long-Term Field Research, Site Characterization, and Data Dissemination in Agricultural Watersheds and Landscapes. The center of the LTAR challenge is the Common Experiment, which analyzes for the local agriculture of each site a comparison of business-as-usual management practices versus aspirational management practices. An example can be found in the El Reno, Oklahoma site, where ARS scientists have been analyzing the business-as-usual versus aspirational grazing land management practices of continuous versus rotational stocking. It has been observed that microbial biomass in soil surface layers decreased in the continuous treatments, but increased in the rotational treatments. Conversely, individual calf weaning weights were higher in continuous treatments versus rotational treatments. In such a case, perhaps there is no one perfect solution, but a balance between the treatments, which would need to be optimized to maintain a sustainable system. This sustainability encompasses consideration for habitats, including avian, terrestrial, and aquatic species, carbon regulation, and hydrologic function. Another example is from Tifton, Georgia, home of the Southeastern Watershed Research Lab, where it hosts the Little River Watershed. This is a 41-year-long study of streamflow water quality that demonstrated that on-field management practices had no effect on the water quality of the watershed in this landscape, as a robust riparian forest buffer was able to provide sufficient removal of the nutrients. Nutrient loading in the local streams is mainly driven by streamflow volume, which is closely tied to precipitation and its seasonality. This information is critical to the interpretation of management studies in the coastal plains of the U.S., as well as necessary for land use planning and regulatory decision-making. These studies are built upon long-term data, but our capabilities to collect data are only the first step. The next is to develop tools and methods to allow for the improvement of water resource management. Satellite remote sensing provides an abundance of near real-time data, which can feed our models and decision support systems. ARS has been critical to the development and implementation and validation of soil moisture products, such as those from the Soil Moisture Active Passive mission. 7 ARS experimental watersheds have been collaborating with soil moisture missions to assist in the calibration and validation of their products, allowing NASA and ESA to produce validated 9-kilometer global soil moisture products that would not be possible without ARS. These watersheds continue to participate and provide the premier CAVAL network for soil moisture remote sensing, as well as for data products from models. But ARS goes just beyond its observations. ARS has developed and validated a variety of models for understanding the nexus of water resources in agriculture. One such model is the Agricultural Policy Environmental Extender Model, or APEX, which is the basis for the nutrient tracking tool. This tool is a user-friendly, web-based computer program developed to estimate reductions in nutrient losses to the environment associated with alternative management practices. APEX was rigorously parameterized and validated to ensure the model computes realistic outputs. The NTT has been initially released by the USDA Office of Environmental Markets, and so far included validated parameters for the Ohio and the Western Lake Erie Basin. It has also been applied to the Southern Great Plains, and the established developmental framework will allow for extension to other domains. Another model, The very well-known Soil Water Assessment Tool, or SWAT, has been updated for improved flexibility and predictive impact of land management practices on water, sediment, and agricultural chemical yields in large complex watersheds. This model has been under continuous improvement for over 30 years, with ARS playing a principal role in its development. Current applications of SWAT include use in the SEEP project to determine the environmental impacts of USDA conservation practices and policies. Data collected in the LTAR project is being used to validate SWAT, which will then be used to model regional and national LTAR scenarios. SWAT Plus is the modeling engine behind the National Agroecosystem Model, NAM, a nationwide model used for research and policy development in the USDA. It has also been a vibrant international community user group with frequent workshops and meetings. SWAT plays a national role, but ARS also is advancing more specific regional models, such as the iSnowball Snow Water Supply Forecasting model. Legacy operational water supply models rely on statistical relationships between stream flow and snowpack measurements at index sites. Unfortunately, those relationships often do not hold up in extreme years. To address this issue, scientists in Boise, Idaho are developing an enhanced real-time water supply forecasting model for water managers in snow-dominated basins across the western U.S. This model assimilates in situ, airborne, and satellite data, and it is computationally intensive and results in large data volumes. The modeling framework has been developed with the intent of eventual cloud deployment. This is a crucial step for tech transfer of the model's capabilities to the everyday stakeholder. iSnowball is being tested for operational reservoir management by water managers in the San Joaquin Valley of California. And this prediction is the obvious next step for data and modeling with component 4C, the measurement and prediction of water-driven agroecosystem productivity and other ecosystem services. Such modeling can be nationally applied as ARS scientists Belsveld did, using moderate resolution and high resolution satellite data to better estimate yield estimates for more accurate yield forecasting by the National Agricultural Statistical Service. Here, you can see the subfield assessment of cornfields in Iowa via a fused Landsat MODIS daily product. Landsat has a resolution of 30 meters, but a 16-day revisit. MODIS has a 250-meter resolution, but a daily revisit. By employing data fusion, ARS scientists have been able to produce a daily 30-meter product for select agricultural sites, also mitigating cloud cover in the process. But some science still requires boots on the ground, such as this example out of Yuma, Louisiana. Sugarcane is not grown from seed, but rather by planting whole stalks, end-to-end in the soil. This process is complicated by cold, moist winters in regions such as Louisiana, which causes lodging and fungal rot. Following a multi-year study, it was determined that this regional agricultural challenge can be mitigated by applying a chemical treatment to the billets, or small sugarcane stalks, that would improve sugarcane yields by as much as 40%. A combination fungicide and insecticide treatment caused the best yield, offering growers an option for increased productivity when climatic conditions are suboptimal for planting whole stalks. These two examples show the breadth and depth of ARS research from satellites to the planting scale, all with the focus of improved productivity. Our last problem area addresses the impacts of climate and land use change on water use and availability. We go from sugarcane to rice. Approximately 11% of global anthropogenic methane emissions are currently attributed to rice cultivation. Scientists in Jonesboro, Arkansas evaluated a rice field with the most advanced monitoring equipment available to test the business-as-usual continuous flooding versus aspirational, alternate wetting drying irrigation methods. There was a substantial reduction in methane emissions by employing the alternate wetting drying method, with a reduction between 36 and 51%. Though the results of this study have been understood in practice, this definitively quantifies the potential for carbon offset trading as it relates its agricultural productivity, informing future management decisions in a carbon-conscious world, and it sets a basis for producers to benefit from the carbon markets. Last but not least, The Agricultural Ecosystem Services, or AEGIS model, is a multi-objective evolutionary algorithm, MOEA, distributed watershed model spanning multiple temporal and spatial scales. It is used to identify synergies in production and ecosystem services. This model has been employed in case studies in Brazil on tropical grazing lands, China for irrigated crops in an arid landscape, and across several row crop landscapes in the US. The model is able to address GEM interactions, including irrigation management, soil water modeling, including runoff, and simulation of conservation effects, serving as a nexus for many of the disciplines discussed in this MP211 retrospective. AEGIS may yet serve as the basis for future planning and forecasting for water availability and ecosystem services.